Okay, so in 5.2, we're going to look at some basic probability principles. And when I say basic, I don't mean to sound like this. Expect that this should be easy. I know that probability can be challenging for people sometimes. By basic, I mean there's nothing fancy about this. And what you'll find is that you can a lot of times solve some pretty complicated probability models if you're able to relate them back to some of these basic tools I'm going to give you. One of them is just going to be simply drawing out the sample space, like thinking about, as long as it's small enough that we can do it. If there's hundreds of different possible outcomes, that might be a difficult task to write out the sample space. But if there's only a couple of dozen and I can actually see them in front of me, it might be helpful for me to look for a pattern. And then the other part of that is going to be a two-way table, which we can also translate to a Venn diagram. I find a lot of times that the Venn diagram tends to confuse people more than the two-way table, but I'll show you that both will work, and they both basically give us the same information. So I want to show you how to use both of those. Now, the warm-up question at the top here, let's think about that. Mr. Smith has 3 children, and at least one of them is a boy. So I'm going to think about what's happening with Mr. Smith, or possibilities. I know he has 3 children. Then it says Mrs. Jones has 3 children also, but it says that her oldest is a boy. Okay, so they give us varying information on these 2 people. And then they ask an interesting question: which is more likely, that Mr. Smith has 2 boys or Mrs. Jones has 2 boys? Or are the events equally likely? A lot of times I'll hear people say, well, they're equally likely. So let's give it a test and see if they're equally likely, or if one is more likely than the other. So let's think about Mr. Smith. He has 3 children. One of them is a boy. All right, at least one of them is a boy. So we know that Mr. Smith possibly could have 3 boys. And just for the sake of arguing here, let's pretend I'm putting them in youngest to oldest. Okay, so the oldest one is the third one there, right? Or we know that he has at least one of his children is a boy. So the only situation that Mr. Smith can't possibly have is to have 3 girls. So he could have 2 boys and then the oldest be a girl. He could have a boy and then a girl and then an oldest who's a boy. So I think these are all the situations of what Mr. Smith could possibly have, right? He has 3 children, and at least one of them is a boy. So I've modeled that. There are 7 possible situations for how Mr. Smith's children could be laid out, right? 2 youngest are a boy, a girl is the oldest, a boy who's the youngest, a girl in the middle, and a boy, and so on. Okay, and then we have Mrs. Jones. It says that Mrs. Jones has 3 children, and her oldest is a boy. So Mrs. Jones's situation could be 3 boys and the oldest is a boy, right? It could be, anything. We have to take away any. We have no 3 girls, and then we always have to have a boy in that third spot. The oldest has to be a boy, right? So we can't have any of these situations here where there is a girl who's the oldest. So these are our 2 situations when we map this out. So now we can go back to their original question. Which is more likely, that Mr. Smith has 2 boys? So Mr. Smith has 2 boys in this situation, 2 boys in this situation, 2 boys in this situation. He also has 2 boys in this situation. And notice it doesn't say exactly 2 boys, it just says 2 boys. So if it said exactly 2 boys, then the first one I highlighted, boy would not be correct. It just says which is more likely, that he has 2 boys. Okay. Now we come over to Mrs. Jones. Where do we find her having 2 boys? Here, 2 boys here, and 2 boys here. So now what would we say? Which do we think is more likely, or are they equally likely? So hopefully we took a look at it. Whether we would need a calculator or not is a different story. But hopefully we said that Mrs. Jones has a better chance of having 2 boys, right? There's a 3/4 chance that she has 2 boys because her oldest has to be a boy. We can't have a girl in that situation there. And then Mr. Smith has a 4/7 chance of being in a situation where he has 2 boys. So interesting, often confusing kind of scenario that we can do if we just write out the sample space and think about it. give pause. So that's what I want to do in the first example here. Give a probability model for this chance process. So what this means is I'm gonna flip a fair coin 3 times, and I want to picture what this is going to look like. So sometimes a probability model would be a table like this, okay? And other times I'm just gonna I could just look at the sample space. So in other words, if I wanted to count the number of times I observe heads, like if I toss the coin 3 times, I could assign probabilities to those particular events. But all I'm going to do here in this first situation is just list out the possible outcomes. There should be 8, since there's 2 outcomes. Call this the multiplication rule. Since there's 2 outcomes every time I toss a coin, 2 times 2 times 2, or 2 to the third, should give me 8 possible outcomes. And I like to list them out this way, similarly to what I did with the boys and the girls in the last example. We could have all 3 heads. We could have heads and then tails. And now there's no way to start off with heads and have heads again, so I'm going to move tails to this position, and we could end with heads. Or finally, we could have heads, and then we could get tails twice. I like to do this systematically because then it helps me not to forget any possible outcomes. Now all I do, I can't start off with heads anymore, so really all that's going to happen now is I'm just going to switch all the letters. I'm going to do the same thing I did here, except anytime I see an H, I'll put a T. So this guarantees me that I get all the possible outcomes just by switching the letters. That makes sense. Okay, so those are my 8 possible outcomes. They all have a probability of 1/8 of occurring. So now we're going to look at a probability distribution. So what we have here are the 2013 AP Statistics exam scores. It's basically the distribution of scores, right? 23.5% score to 1, 18.8% score to 2, and so on. 24.9% score to 3. Okay, and so on. Show that it's a legitimate probability model. In order for it to be a legitimate probability model, it means that all of these categories have to be mutually exclusive and exhaustive, and the probabilities have to add up to 1. So if 0.235, so by mutually exclusive and exhaustive means there's no other scores you can get besides a 1, 2, 3, 4, 5. And there's no way to get a 1 and a 2 or to get a 1 and a 3 at the same time. You have to be in one of these categories, and there are no other categories that you can possibly be in. Like you can't get a 0. So 0.2 or a 6. 0.235 plus 0.188 plus 0.249 plus 0.202 plus 0.126 should equal 1. And that proves that it's a legitimate probability model. Okay. Find the probability that a chosen student scored a 3 or better. So a lot of time, I enjoy probability a lot. It's probably my favorite thing to study and to teach. But oftentimes it becomes a reading comprehension issue. We have to be very careful about how something's worded to answer it correctly. So I want to make sure I get what they're asking for. The student scored a 3 or better. So sometimes people might look at this and just say, well, that's a 4 or 5. It's talking about all of these possible outcomes. That's a 3 or better. So the probability that they scored a 3 or better would be 0.249 plus 0.202 plus 0.126. That would be one way to get it. The other way we could do it is we could add these two together and subtract that from 1. Okay, we can do either one of those will give us that probability. So in both of these cases, I get 0.15 or 0.577. Sorry, can't see my calculator. 0.577. Okay, so that's one way to look at probabilities with a table. Okay, now we're going to use a two-way table, and a lot of times, if you have a probability problem that's just a narrative, and they give you some numbers, a great thing to do, I often encourage my students, is to make it into a two-way table. Draw the two-way table out, take the information they give you, and make the two-way table if you can. It's a great way to organize the problem in this situation, and we'll do that in the next example. But in this situation, they give us the two-way table, so you can see, and we have we looked at two-way tables earlier this year in Chapter 1 when we talked about conditional distributions and marginal distributions. So this is going to we'll start to apply probability and chance situations to those two-way tables that we've seen before. So suppose we choose a member of the sample at random. Find the probability that the member is a high school graduate. So very simple. It's just one outcome. There's not multiple things happening here. Where are the high school graduates? There are 310 of them out of a total of 500. Okay, so that's straight away how we get that probability. So we get 0.62 or 62%. That is part A. Part B. Is a high school graduate and owns a home. So I need two things happening there. And a simple word like and or makes a huge difference here. So this time the person is a high school graduate and they own a home. So it's not all 310 of these. I'm only looking at these 221. And it's out of everyone, right? It's a member of the sample at random. There's nothing conditional about that particular question. So it's 221 out of 500 would be the probability that they are a high school graduate and they own a home. All right, so probability that they are a high school graduate and own a home, either 0.442, or if you like percentages, you can say that as well, 44.2%. It doesn't, to me, those two numbers mean the same thing. People ask me that all the time. Do you want us to write a percentage or a decimal or a percentage? And it doesn't matter as long as you put the percent sign there. Right? Is a high school graduate or owns a home. Okay, so now we want to be careful with this or conjunction. Right? We have our high school graduates, so they can be either one. So it's everybody that's a high school graduate. So I can see that there's 310 of those. Okay, but there's or owns a home. So these folks here are also included in this, right? Because they're homeowners, even though they didn't graduate high school. And then it's still going to be out of the total. Okay. So sometimes what you'll see, you'll see this expressed like this. You'll see they'll take that they're a high school graduate. We just add them together. And then we would subtract away where those two things intersect. So you'll see a lot of times they might write it like this. 310 out of 500. Those are the high school graduates. And then they say, okay, and then we take the homeowners, which is 340 out of 500. The problem with that is that we just counted these folks twice, so we have to subtract it away. So you'll see that as a formula on your formula sheet. And this is our handy-dandy AP Stats formula sheet that you would get if you take the AP Statistics exam. So the formula that I was just referring to right there is listed here. Okay, probability of A or B. That's what that U means. It means the or symbol. So we take probability of A, which is the probability they own a home, plus the probability of B that they graduate high school, and then we subtract away that overlap. Okay, so you often see it that way. When I look at it, I kind of just do that in my head. I say, well, here are my high school graduates. There's 310 of them. And then I go get the other piece that I'm missing. I already know that I had this 221 here. I don't need to remember to subtract it, but sometimes that will be helpful. Okay, so 429 out of 500 or 0.858. Okay. So now let's look at the same information from the two-way table, but let's look at it in the form of a Venn diagram, okay? In my Venn diagram, so we have these symbols here, all four of these numbers, the 89, the 221, the 119, and 71, they all live up here in the two-way table as well, right? 221, 119, 89, 71. The 221 is the probability of both home ownership and high school graduate, so that lives in this football in the center. That's where both of those items occur, okay? The 89 is going to be people that graduated high school but do not own a home, right? So we come back up here. So these 89 people graduated high school, but they don't own a home. So in the Venn diagram, they're going to live in that part of the circle. So because they are graduates, but they're not in the blue circle here where they own a home. Then we have the 119 here who did not graduate high school. They're not a high school graduate, but they own a home. So they live here. And then these 71 here never graduated high school, don't own a home. They're both of those. So where I'll notice that people will get confused here is they'll put like the total 221, 119. They'll put that in one of these boxes. Those numbers don't go anywhere. That's the one thing you want to notice. And when you look at the Venn diagram, these particular numbers here You won't see them anywhere. They're not going to occupy their own particular space in the Venn diagram. All 4 numbers are going to have to add up to 500. So when I'm creating a Venn diagram, what I like to do first is put this number in. I find that intersection of what the 2 events are, and I plug that in the middle first, and then I build my way out from there. So that way I can subtract it away from whatever that other total was, and we can find it. So as long as we have at least one of these boxes in the middle here, one of these values, we can build out our Venn diagram. So let's give it a shot in the next example. Okay. According to the National Center for Health Statistics, in December 2012, 60% of U.S. households had a landline. Okay. 89% had cell phones. And then 51% had both. So hopefully we can see the makings of a Venn diagram. We're going to use a two-way table and also a Venn diagram. We want to do both in this scenario. So like I said, the two-way table is probably the easier one, at least for my students most of the time. They feel like that's an easier one to look at. So let's start with that one. Now our 2 events are going to be have a cell phone and have a landline. So I'm going to use the letters C and L to represent that. So in my two-way table, we're going to say we'll start with traditional landline since that's what they had. Instead of writing it out, I'll just save some space. Okay, so I'm going to have folks that have the landline and folks that do not have a landline. We'll call that landline complement. Okay, and then over here we have folks with a cell phone and folks that do not have a cell phone, or households, basically what they're counting. This is how I'll fill out my two-way table. Now, they told me 60% have a landline. Where does that 0.6 live? It's down here. This is everybody that has a landline. I'm not paying attention to whether they have cell phones or not. Okay, 60% landline, which means right away, look, 40% don't have it. I want to try to start to build out and fill out anything I can so I have 100% of everybody. They either have a landline or they don't. Those are complementary events. Okay, now we go to the cell phone, right? 89% had cell phones. So where does that live? This is the total of everybody with cell phones, which means the other 11% don't have it. Okay, now here's where I'll be really stuck. If I don't get one of the 4 of these values, I'm stuck. I can't go anywhere else with this two-way table. It's not going to be helpful in solving a problem, but they give me the percentage of people that have both. If this is 51%, now we basically have everything else, right? 60% minus 51% means that 9% live here. These are people that have a landline and don't have a cell phone. Then we have 89 minus 51, that's 38%, 0.38, right? 51 plus 38 gives me 89. They have to add up. So these people here have a cell phone, but they do not have a landline. And then finally, there would be 2% that don't have either, 0.02, right? 40% minus 0.38 or 0.4 minus 0.38 would be 0.02. And then now we can use this and we can answer pretty much any question they would want to ask us. And this is where we go in the next section. Things get a little bit more complicated. We say, we might ask if the 2 events are independent, if they affect each other, or what's the probability that somebody has a landline if we know they already have a cell phone. So we start asking more complicated questions than that. We don't have any such complicated questions here. Just a two-way table in the Venn diagram, and then we'll answer some questions based off of those. So what would the Venn diagram look like then? Okay, I always put my 2 circles in a box. I'll see sometimes my students don't do this. They just draw the 2 circles. I think it's really important that you put them in the box because then you can acknowledge what's happening out here. This 0.02 people that don't have either, right? We don't want to forget about that proportion. We're talking about people either that have landlines or that have cell phones. And like I said before, I like to start with the fact of the people that have both. This way, I don't want to do something like this. I'll have people go and they'll put 0.6 here, and then that's wrong. Okay, the 0.6 is the whole circle. This whole L circle is 0.6, which means this over here has to be 0.09. I need the 0.09 and the 0.51. That adds to 0.6. Okay, the 60% of folks that have landlines. The cell phone circle, that has to add to 89. So that's how I know this would be 0.38. So both of these tools give me the same information, just a different way of looking at it. I've found, some people, maybe more visual people, like the Venn diagram better, but the mistake I see people make is they'll put, they'll do something, like I said, they'll do this. They'll put 0.89 here, and then you're never going to be able to get your probabilities correct in any question that we ask. So make sure you build those out right. All right, find the probability that the household has at least one of the two types. Right? So that's part C, not B. At least one of the two types. So it's basically everything in here. It's everything but this. So the easiest way to get that answer would just be 1 minus 0.02. Right? If they have at least one of the two types, that means they could have the landline and not a cell phone. That'd be anybody that's in here, anybody that's in here, anybody that's in here. Those are all wins. So I either add all those up, or I just subtract the 0.02 from 1. I think that's the easiest way to get to it. Okay. Find the probability that the household has a cell phone only. So again, this is going to be really easy. They only have a cell phone right here. Okay. This is the overlap of landline and a cell phone. So I can get these values very easily out of that Venn diagram if I know what the letters stand for.